So a while back, I had just finished reading a chapter in a book on heuristics and methods for maze solving, and I thought it'd be really cool to actually implement a few of them and test them against each other. As I was planning this little competition, I ran into the issue that I didn't have a maze, and for that matter, even if I did, testing each method against one singular maze would make a pretty distinctive bias. It seemed I had to now learn a whole new skill to even get started with practicing the knowledge that I just learned from that book. At first, this was rather disheartening, but I quickly fell in love with the beauty of a self-designing maze, and a lot of the methods of generating a maze are rather intuitive. In this video, I want to talk about that question, like how does a maze get designed and how can I make one? I think it's important to first of all define a maze. There's lots of different types of mazes, and for the purpose of this video, I want to keep it as simple as possible. For this reason, I will choose two main rules as a defining factor of what makes a maze a maze. Firstly, every maze needs a start and finish point, otherwise there's no real way to tell if somebody has finished our maze. And our second rule is that every square on our grid has to be accessible by any other square. This is easy to see why it's important if we have no physical way of accessing the end block from the start block as shown on screen. But even if just some unimportant part of the grid is not accessible, it makes our maze unneededly easier and limits the spots we can choose for our start and finish blocks. Idealistically, we should be able to choose any two start or end points and solve from there. We can see that on a small grid like this, we can easily plot out a new maze by just putting a line here and there and placing a start and finish. This is our maze. Obviously, we want mazes bigger than this, and it takes us mere seconds to simply solve the one on the screen with our eyes. Unfortunately, if we try to increase the grid size to say 40 by 40, we get something like this. And it's not entirely impossible to populate a grid here by hand, but it will be super prone to errors and pretty poorly made. What we need is a systematic way to populate this maze, and we're approached with the question of how do we do that? And there are plenty of methods of generating a maze, and I don't have time to talk about a lot of them right now. It's honestly super fun to watch mazes get generated with different methods because each has their own personality and style. But a lot of the time there's this pretty common idea. If we carve out the maze as we are walking through it, then every place we've been to will be accessible. Imagine you want to make a corn maze, but you forgot to plant your corn in any distinguishable pattern. If you simply walk through your cornfield, cutting everywhere you walk, you can make really whatever pattern you want in that cornfield. And best of all, every place will be accessible from the start because you had to get there to start cutting there. So in essence, in order to make a maze generator, we can simply create a little corn farmer in our program and have him walk through the grid, placing or taking down walls wherever he needs to. And for simplicity, we can limit ourselves to not revisiting any visited grid piece, and that way, no matter what happens, we will always have a completed maze with every grid piece incorporated. Now, there are a few specific methods for this kind of running through our maze idea, and the one I want to talk about in this video is probably the simplest, being the depth-first maze generator. In a depth-first maze generator, the maze solver will go as far or as deep as it can in our maze it's constructing, and will only stop when it's backed itself into a corner. Upon backing itself into a corner, it will retrace its steps until it can find an unvisited grid block in the vicinity of whatever block it's standing on, and then will continue along that path as long as it can. Upon repeating this process enough times, it will have ran into every block on our grid and eventually retrace all the way back to the start. And then we have our maze. So I just talked a lot, and now I want to put a visual on the screen. We can start with an empty grid and then place a player. And we can do this whenever, but I'm going to place my start and finish blocks right now, so we can just get that out of the way. To finish our setup, we can go ahead and place walls around the player just to get some obstacles around the grid. And now we're going to find all the adjacent and unvisited blocks that are next to our current grid piece. We'll then choose a random one to go to and place walls around that grid piece and cut away any walls between us and that grid piece. And then we simply repeat this process until we walk into a corner. Now that we're cornered, we're going to back up, find an adjacent piece, and then go there, and repeat the process until we walk into another corner. And now at this point, we back up, find another adjacent piece, and then now we back up a lot until we get to the nearest adjacent piece on our grid, which is right here. And then we simply finish off the maze and we can go back to the start. And now we have a maze. And that was really straightforward. Over the next portion of this video, I'm going to go into how we can take this intuition from our brain and put it into a programming language like C++. If you don't care about that, I want to thank you for watching, and I hope this was a good enough explanation for you. And consider sticking around for when I upload more content like this. If you are interested in the programming aspect of things, I'm going to go ahead and swap over to VS Code, and I'll see you there. Okay, so what I have here is a basic setup for a program. I have a couple extra includes though. I have CMath, vector, and then this is what I'm using to display my maze. I'm not going to actually go into this on this video. So if you kind of know SFML, then you should have no trouble. Or if you know any other way of displaying mazes or displaying graphics, then that's great. I'll have my code in the description, so even if you don't really understand and you still want to figure out like how to display it in the way that I do, you can look there. So we're gonna go ahead. I'm gonna try and kind of get this kind of out in the way that we described it. First of all, so we need a grid. So what I'm going to do is I'm going to define the dimensions of our grid. I'm going to say constant int in y. This will be the vertical size of our grid. I'll set it equal to 50. And then I'll say const int in x equals in y. This just means I want a box. I could set it to whatever. It doesn't need to be a box, but whatever. Honestly, I probably don't need this, but for simplicity's sake, I'm going to make a new struct called pose, which is just going to hold an xy position. So int x and int y. And then here's where the magic happens. So I use a lot of like bit representation for booleans in a way here. If you don't really know too much about the bits and bytes of everything, I want to make more videos on that or even write about it, but you can kind of figure it out as you go along. So I'll write the bit representations of these. I want a way to represent whether we need like a wall on top of a grid or on top of a block or on the left or the right or the bottom of a block. So I'm gonna use these bit masks to kind of figure that out. So we'll do this, and then what I'm writing on the right side here are just what this looks like to our computer. So there we go. As you can see, like each different bit it's kind of just shifting over one. That's perfect for what we want. And then I also actually want 4 more of these. Not for directions, but just for general information. So I want a start tag that we can put on a block, an end tag, a current tag, and a visited tag, just so we have ways of knowing where everything is through our grid. And then actually now we're going to make the grid. So we can say that int grid in y in x equals 0. And so this just brings us a matrix of height y and width x all assigned to 0. So that's perfect. And then we're going to make a frontier. So we're going to make a vector, a list of positions and coordinates called frontier. And this will just tell us like all the blocks we've been to that we still haven't backtracked from. So we have like a path back to where we start our maze. And then we can go ahead and get started. So what we'll do is, first of all, we're going to start by defining a start position. And we'll just set it to any random place on the map. So start.x equals rand modulus in x. This will set our, so we'll choose any random number between 0 and in x minus 1, which is what we want. And then start.y in y, same thing. And then we'll say that grid start.x, actually start.y, start.x equals or equals start. And so this says or equals start. This says that if this basically guarantees that this bit will be flipped on, and that's our way of saying that, hey, if this bit is on, then this is the start block. Okay. And then we'll say pose end, but we won't actually assign it here. And then what I'm about to do is going to make it a lot easier for choosing a good endpoint in our maze, but it's not necessarily required. It's just something that I found worked. And then we're going to make a pair of backtracks as well. So we'll set a bool called backtracking equals to false, and then backtracks another list of positions. And then we'll go ahead. We're going to make a pair. We're going to call it current, and we're going to set its initial value to start X and start Y. And that means we're going to generate the maze initially from start X and start Y. And then pair, actually, no, that's good. And then we'll go ahead, we'll start our frontier, we'll push back that a new pair int start.x and start.y. Perfect. So we have this list, and this is kind of like we spawned in our player, we have our player on the start block, and now we're starting to look for those movements where we branch out. So we'll say that while frontier.size is larger than 0, we want to keep this loop running, and so it will visit every block. And then once this frontier.size is 0, we've been to every block, there's nowhere else to go, terminate, and we'll continue on in our path. And so there is actually one thing that we want to do at the end where there is nowhere else to go, and we'll set that up later. So terminate and populate grid. And that's what we want right now. Or not while, sorry. Can't say is, we can't say, we'll say instead, sorry, is if frontier.size, so once this is done, we'll say if frontier.size equals 0 and backtracks.size is larger than 0, we'll run this. And this will just give us an end block. And we'll go into this in a second. Okay, so now we're going to populate the grid. And right now we're at that area of that visualization where we're looking for all the adjacent blocks. And so we're going to go ahead, actually, we're going to make a function to find the adjacent blocks. And we'll scroll up here. It'll be in, it'll return an int. We'll call it validors, whatever you want to call it. And we'll take in a coordinate. Okay. I'm going to make a new variable. Valid directions equals in or south or west or east. So right now, all of these bits are set to 1 and nothing else. And then we're just going to set up the like barrier conditions and all that. We don't want to be able to go to a block that we've previously been on. So what we'll say is if x is, actually we'll say if y is less than or equal to 0 or grid y minus 1 x does not equal 0. Then valid directions does not, or and equals not north. So if we are at the very top of our grid, we shouldn't be able to move north. And if we've already visited the block above us, we shouldn't be able to move north. That makes sense. Same thing. If y is larger than or equal to in of y minus 1, if we're at the very bottom, or we've already been to the block below us, does not equal 0, because it will only equal 0 the first time we go to it, or before we go to it. Valid directions and equals not south. And then I'm going to go ahead and copy and paste this. We're going to have to change the x's to, or the y's to x's, but we're going to do this for south and east. And then here, x minus 1 and x plus 1 instead of y minus 1, whatever. So If we are on the very left side of our grid, then we don't want to be able to go west. And if we're on the very right side of our grid, then we don't want to be able to go east. And if we don't want to be able to move to the right, if something's on our right, whatever, you get it. And then we'll just return valid directions. And so this is just returning any of the directions that we currently can go to without something in our way. And so we'll go back to our main function, and we want to get the directions that we can go in. So we'll say int directions equals valid dirs current dot first and current dot second. And then I made a typo. If there is a direction for us to go in, if direction does not equal 0, we don't need to backtrack, so we can say backtracking equals false. And we're going to go ahead and count the amount of directions that we can go in, and this will help us figure out the random direction we want to go in. So count plus equals directions and in modulus 1. So if it's greater than 1, then it'll, or if it's greater than 0, it will just return 1. And then we're going to repeat this, and this will just let us know how many valid directions we have available to us. Perfect. Now, we're going to go ahead, we're going to get a direction by saying int direction equals pow to a random number between 0 and 3. Here. Perfect. And this works because these are powers of 2. This is 1, 2, 4, and 8. And, well, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. So that works. And this will get us a random direction in that form. Now, we can go ahead and say, while we want to check in case it gave us a number that we can't actually use, we'll say while directions and direction equals 0. We're just going to reassign until our direction that we chose and our directions is a valid direction, whatever. And actually, I'm not sure if we need this count. I kind of had an idea, and then I realized I don't think we need it. So we're going to attempt to remove it, and we'll see if we need to re-add it. And then now we can actually choose the actual moving part of our code. So what we can do is say if direction and in does not equal 0. So if we're trying to move up, then what we'll do is, well, we want to remove any walls between us and the grid above us. So we can say current.second, current.first, and equals not north. So we're removing the wall above us on our grid, but we also have to remove the wall below us or below on the bottom of the grid above us. So we'll say current.second minus 1. So this is a grid above us that we're trying to go to, and we want to remove the south wall. Now we can say that our current grid, current.second, current.first, is no longer and equals not current. It's no longer our current block. I'm not sure. We're going to reset this here. So current equals pair, current.first, and current.second minus 1. So now our new current is this, and we can go ahead and say grid current.second, current.first, or equals current. It's now our current block, and or equals visited. And then we can go ahead and put it on our frontier. Stop pushback, pair of a position, current.first and current.second. So now it's added to our frontier, so when we backtrack, we'll know exactly where to go. And then we just need to do a couple more things. We need to say current.second and current.first, or equals in west and e. And so this is just putting walls around us everywhere that we didn't just come from. And then perfect. So we can repeat this process actually by saying else, by saying else if. south now. Same thing. Now we just flip the signs here. We're moving down. So +1 and then +1. Perfect, perfect, perfect. And then here we need to go ahead and add a south wall and then keep this top wall because we get rid of the top wall here. So hopefully that makes sense. I'll see if I can explain it better. And then same thing. So let's go to the west. Now we're going in the X direction, so we're going to go to current.first. To the west means -1, and current.first -1. We're moving to the west, so we want to remove our west block and the block that we're going to's east wall. And then we want everything but the east wall reactivated on that new block that we're going to. And then same thing. East. Oops. Swap these. Swap the signs. And we now want east instead of west here. Okay. And that's actually it for our increasing the size of the frontier and adding walls and everything like that. If there is no direction, if we are in a corner, we will say else. And we will say, first of all, this is going to help us find a good finish. We'll say if backtracking equals false, backtracking equals true. And so this is just the first time we start backtracking, and this means it'll be in a corner, which I like to have my endings in corners. So you don't really need that, but push back, and then we'll add it to the backtracks, the list of backtracks that are in corners. Back.first and frontier.back.second. Good. Now we'll actually deal with the whole going back thing. First of all, the block that we're currently on, we will no longer be on for long because we are going backwards. Comma instead of dot. So we'll say and equals not current. Okay, so it's no longer a current block according to that. We're going to pop back. We're going to remove the last thing to be added to frontier. And we'll say that if the frontier's dot size is larger than 0, then we can go ahead and make a variable of the new frontier, the block we're going back to, its position. And we can say that current is now equal to pose.first and pose.second and grid current.second and current.first or equals current. Perfect. And then we really only have to finish up here for the terminate and create an end spot. So what I'll say is I want to set up a couple loops to kind of check through all of the backtracks. So I'll say for int I equals 0, I is less than backtracks dot size I plus plus. I want to get the distance from the start to the backtrack, so I can find the one that's the furthest away from the start to make our finish. So avs start.x minus backtracks I.first. Good, and I'm doing Manhattan distance instead of main distance, or instead of mean distance or whatever. Start.y.second. This is just getting the amount of spaces to the left or to the right, plus the amount of spaces up or down. And I think we just put this in more. Whatever, we'll do it like this. Now, I'm going to set another int up here, int longest equals 0, and int longest index equals 0. And then if distance is larger than longest, then we want to set longest equal to distance and longest index equal to I. And then once we're done with this loop, we'll say that grid backtracks long index dot second backtracks long index dot, sorry, I forgot, long index dot first, or equals, I want to say just or equals end. Yep, or equals end. And then perfect. We can set n.x equals backtracks longest index dot first, and n.y equals backtracks dot second. And then just go ahead, clean it up a little bit, clear, and then return 0. And this is actually our entire code. This will make the maze, and if we don't have a way of displaying it, then it doesn't really do anything for us, quite frankly. But it does it. It does it. It makes it. And so I'll show the finished example on screen in a second. And if you want an example of how we can display it, I will put that in the description so you can go check it out. And let's get back to the maze. Maze generation algorithm with just a little bit of visualization. This is a 100 by 100 grid. I have it sped up a little bit. It took about 5 minutes to generate this maze. As you'll notice, one of the biggest issues with this is that it creates like really long straight lines. I mean, that's pretty much the definition of a depth first algorithm. Honestly, I prefer mazes that are more interconnected, like there's more than one solution or something like that. And there are other algorithms that implement that. This is not one of them, unfortunately, but I think it's still a pretty amazing algorithm, and it's really fun to watch. And so I hope you enjoyed this, and I hope you were able to implement it, or maybe you have an idea for a more advanced algorithm or something like that. Thanks for watching, and I will see you guys next time.